So it is my great pleasure to introduce our next speaker here. We're going to take a little bit more of an entrepreneurial perspective. So I'm going to introduce Odilon Lemieux. He is the founder and president of Borum Energy Solutions, which is a Canadian energy solution firm that specializes in microgeneration and home wind turbine technology in North America. So before founding Borum Energy Solutions, Odilon has spent much of his professional career as an engineer and consultant, particularly in the realms of electrical engineering, applied sciences, and engineering management. And so with that, I would like to hand it off to our next speaker, Odilon. If you are ready and your team is ready, please go ahead and take the floor.
Well, good afternoon, good morning, good evening to all of you. My name is Odilon Lemieux. I'm the founder and Chief Executive Officer of Borum Energy Solutions. What I want to cover with all of you in the next 20 minutes or so is how our microgeneration wind turbine, what it is, and how it's been designed for the Arctic. And it's a viable solution for numerous applications in terms of energy generation or electrical generation. Having said that, the first thing that I would like to cover is our firm. So I'll spend a few seconds here in the next slide what our firm is. So it's a private corporation. We do a lot of R&D. We focus on how to deal with the harsh condition of the Northern Hemisphere. And we'll talk about that, how we deal with that. Our firm designs everything from the tip of the blades to the tower base and everything in between. What is relevant here is we design the blades and we design the generators, and by coupling them very well, I guess, we can improve the yield of the electricity production compared to competitors or other wind turbines. We are very close here physically to the University of Waterloo, so we have ongoing research activities with them to improve our turbine, whether it is for the blades or the generators, for example. Now, when we talk about micro generation, it's important to understand what it is and what it's not. Microgeneration is defined as the means of generating electricity very close to the point of consumption. Now, this can take place in the form of solar, bio waste, for example, or wind. On this chart here, what we have is a standard distribution system. On the left-hand side, you got the different power generation, nuclear, fossil, wind, hydraulic, and solar banks, I guess, through a transmission, distribution, and getting to a dwelling, a small dwelling. The microgeneration system, in this case, can be in the form of wind or can be the form of solar, right? In fact, they complement each other. They are usually not connected to the grid, and the electricity produced reduces demand on the grid. And as a result, that for numerous rural dwellings can reduce their electricity cost, right? Now, this microgeneration, energy generation can be used for heating or electricity generation for dwellings. It can also be used because it's portable for camps, small camps, or electronic equipment in a very remote setting that need ongoing energy generation to support their operation. The next thing I would like to do here is give you a little video of what this microgeneration turbine, and the one that we want to present is called the Anora. Well, it looks like we probably want to come back to the NR a little bit later on. So what I'm going to do, we're going to go right away to the challenges that any type of system face in the Arctic. And I'd like to talk about that in more details. The top four, from our perspective, and there may be a few additional ones, the top four are the temperature, the wind, steady wind, gust wind, and we're also going to include the icing in that category. The third one is the corrosive environment that's present in the Arctic. Lots of areas are close to the ocean or areas where it's salt water, so the air would be salty and create a corrosive environment. And finally, the logistics of bringing a microgeneration turbine to the point of electrical consumption, as well as its installation. So let's start with the temperature. So the turbine design integrated, to start with, very low temperature requirements. And I'm pleased to say that our turbine has been tested independently and very successfully to minus 50 C, which covers most of the areas in the Arctic and subarctic elements. The blades, our carbon fiber, are not affected by temperature. And furthermore, we have no mechanical system on the turbine and the tower that can be negatively affected by the temperature. I also like to point out that we have no electronics on the turbine. Reason for that is electronics, circuit boards don't do very well in cold temperature. Furthermore, it's clear that if a circuit board breaks down in the middle of remote location in the Arctic or subarctic, it's difficult to probably find somebody to fix it or troubleshoot it. So in order to improve reliability and availability of the system and ease of maintenance and repair, we eliminate all electronics on the turbine itself. I'm going to continue here. I am not sure if everybody can see my slides or not. Or if
Mr.
anybody,
Lemieux, sorry to interrupt. I will jump in and I can share the slides on my end. So I'll pull those up right now.
Well, thank you very much.
No problem. You bet. And in addition, the video is working on my end as well, so I can play that whenever you're ready.
Perfect.
Well, thank you. Can we do let's take a break here and to deal with these technical challenges. And let's play the video and then we'll come back to the next challenge.
Okay, you bet. Here is the video.
Thank you. All right, so we've talked about the temperature. So the next, if we can move, thank you. We're going to talk to the next challenge that we dealt with. The next challenge is the corrosive environment that's present in the Arctic and subarctic. So we've integrated a protection against the corrosion within design. Obviously, the blade's been carbon fiber that doesn't corrode. The turbine itself is made of anodized aluminum and galvanized steel. The tower itself is all made of galvanized steel. To validate that our design can support an anti-corrosion for at least 20 years, we submitted the turbine to the B117 standard anti-corrosion test that's used a lot by the military, and I have to say it was very, very successful. So from a corrosion environment, this turbine is good for a minimum of 20 years. If we want to move to the wind, well, here's the thing about the wind. Wind, there's steady wind, there's gust wind, and there's icing that we have to consider. So the first thing that we want to look at is that the blade structures have been tested independently to withstand 190 kilometers an hour, which is about 118 miles per hour, steady wind. And I have to say, even at that type of wind, the wind applies a lot of pressure on the blade structure. The blades did not break. And in fact, the blades return to their initial shape once that pressure was removed. The tower structure itself meets, if not exceed, the same standard. So in terms of gust wind, and I think here the technical problem is that this is a previous set of slides, so there's a few things missing, but we'll make sure that we provide the updated presentation. But at the end of the day, the tower structure and the turbine can support and will support gust wind of up to 120 miles per hour. If we want to go back one more, the other thing is it will withstand icing, and icing here needs to be considered not only, for example, the blades, but also on the guy wires for the turbine. So the blades themselves are painted black, so they can absorb the energy from the sun when it's sunny, and they also we put a compound on it to help remove the chance of icing. There's also icing on the tower and the guy wires that need to be accounted for. And we can support up to, the system can support up to 30 millimeters of icing on the turbine, which is pretty high, unlikely to be seen in Northern Canada. The last thing I want to say, and I know for sure here that this is an old slide. We had nice pictures that deals with the Alaska, but basically the tower system and the whole system is shipped in modules. All right, and the way it's done is the turbine and the tower are assembled horizontally. That can be done with the common tools found in the house. Okay, and the tower is a tilt tower with guy wires. And the tower, once assembled horizontally, can be raised vertically by a numerous type of vehicle that can be easily available in the Arctic region. Snowmobile, ATVs, track vehicles, pickup trucks, and we also have a configuration where one can use a manual winch. Okay. The reason this is feasible, one of the reasons feasible is the turbine is fairly lightweight since we maximize the use of aluminum for the turbine itself. And so it's really light compared to others, and that ease the raising vertically the turbine. It works the other way around. The system is portable. So if this is a setup where the point of energy electrical consumption needs to move, like a camp or research instrumentation or whatever, tower can be brought down horizontally, dismantled, put back in the shipment containers, and brought to the next site where it can go up the same way. So when we look at the ANORA here, what we have in this diagram or this schematic, we have the tower poles coming from the bottom, aluminum, galvanized steel, very lightweight. We have the furling system with the vane totally on the left-hand side, okay? And the actually the furling system components attached to the turbine, that's made of galvanized steel. Now, this furling system has no springs, no coils, nothing that will break, nothing that will fatigue over time, okay? And not to reveal the secret sauce, but it basically relies on gravity to work very well. It works very well. And as one of our engineers said, if we lose gravity, we have a bigger problem, not just the turbine. The generator behind it and the nacelle is all anodized aluminum. So is the hubcap here, the cone, and you can see the carbon fiber blades on this diagram. So that's a bit the structure of the Anora. If we go to the next one, so if we look at the summary of the challenges here, then what we have, if we go to the next slide, thank you. So what we have hopefully covered is that our turbine is designed and tested to address the biggest of some of the big challenge in the Arctic temperature, -50, wind up to 120 miles per hour, corrosive environment, logistics, and installation. What I like to also point out today is we are a research and design organization, so we leverage and make sure we meet various standards, whether it is on antennas, building code, electrical code, obviously, as well as, for example, the IEC international standard. It's called the 62400-2. I'll spare you the details, but it's an international standard on small wind turbine or micro generation wind turbines that we're there to. So our business model, anyone can order one of our turbines on the internet, it's available. But we also support and looking for distributors that can be resellers or value-added resellers in the Northern Hemisphere. So at the end of the day, microgeneration, the Anora, is basically a premium, affordable microgeneration wind turbine. We kind of borrow the IKEA model, some assembly required by the end customer. We will have a virtual booth later on today, and I welcome all of you to visit us and talk to us about your plan, and we'll answer any questions you may have. Now, at this point in time, I'm assuming we have a few minutes left, so I'll turn it over for Q&A.
Great. Thank you so much, Mr. Lemieux, for that, a very technical perspective, as well as an example of a business that has transformed challenges in the Arctic into solutions and into an opportunity. So thank you so much. As Mr. Lemieux mentioned, we can open it up for questions. I don't currently see any in the chat. I'll check with our Executive Director, Church. Do you have any texts that have come into you? Okay.
I have one that's come in. And those folks who are familiar with our Cousin Partners Roundtable, this is fairly standard for us to receive questions via text. And so this question just in, thank you for the presentation. As I look at what you are developing for the Arctic region, or it's capable for the Arctic region, have you looked at how you can work with specific communities to use these technologies for remote power generation by understanding the power needs of the local communities and where you could potentially use this technology?
Yeah, that's a really good question. We are in the product business. So our generation right now, as I said, it's can generate between 1 and 3 megawatt of power per year. It scales up in the sense that depending on the local community needs, one can install multiple of these turbines to meet their needs. So from that perspective, we're very much looking forward to work with local communities to see what their needs are. But our system can very easily scale up. And normally what we find is these organizations are interested in installing one to get a feel for how it works and what their wind profile is, and then scale up moving forward.
Sir, I have another text, and I'm not sure if you had covered this earlier, but let me offer this to you. Thank you for that reflection. Let me offer you another text, if I could, on another question. Right now, wind turbines do considerable harm to avian populations nearby. The Arctic is a region where bird populations are substantial because it's a nesting ground for many avian species. Is there any technologies that you're looking at that could reduce the risk to avian populations that would be nearby, nesting nearby any established wind turbines?
Yeah, a very interesting, very topical, I guess, question. Okay, the way we address that, and it's an important item to address, is currently the blades are all black. Okay, and what we do for this kind of environment is we add white stripes in the middle of the blades across all three blades. And there's some interesting research that shows that that kind of painting, if you want to, when it rotates, will basically not scare the birds, but tell the birds to move away from it. So that reduces the impact. Secondly, contrary to the large utility-based turbines, our blades are quite small compared to them. So the probability of hitting birds or birds hitting the blades are very low. So that's a bit how we are dealing with that, is through a paint pattern that's been proven to be very effective.
Actually, I have a follow-up text to that, so thank you for that. Sir, have you thought of generating a noise element that the birds would react to?
Good question. There are some noise generators available today for birds. I mean, the airports are using them, for example. As an entrepreneur, I'm focusing on a product that requires the market. Obviously, if somebody wants to add a bird generator, a noise generator for birds, to be fair with you, there's a lot of them available in the marketplace. Now, what we could do is use the turbine to generate the electricity for that noise generator.
I'm sorry, I'm trying to monitor both screens here, so thank you for that. I have a thumbs up for that reflection, sir. Ellie, that's all the text I've received. I thank the presenters. Great set of reflections. Back to you, Ellie.
Thank you, Church. I echo that. Thank you so much, Mr. Lemieux and your team, for this presentation. It's a really great perspective on the entrepreneurial level. And as you mentioned, I'd invite everybody to visit their booth at our virtual solution showcase that is taking place this afternoon. And again, of course, you can visit our event hub to access all of those booths. So thank you again. I know everyone is joining me in a virtual round of applause.
Thank you very much for the opportunity.